All right, we are going to finish off our 9.1 notes on sequences and series, and we covered pretty much everything about our sequences in class. We are going to talk today about summation notation and our series. So summation notation, mentioned very briefly at the end of class, uses the Greek letters sigma. That's this one that looks like a capital E here. And what we do is we write the sigma. It means the sum of this sequence rule right here. That's our argument a sub I. And we are using I as our index of summation. And you can use I, you can use J, you can use K. Typically we use I, but it can really be anything. I is the index. Down at the bottom of this sigma notation is what we call our lower limit. So typically that starts at 1. It doesn't have to. It could start at 2, 3, 4, 5. Most of the time it's going to start at 1. That's our lower limit. And then n up at the top, that is our upper limit. So we're summing the first terms 1 through n. So this summation notation we have here is just saying a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way up to a sub n. This helps us define what a series is. So if we have some sequence, a sub 1, a sub 2, a sub 3, blah, 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 a sub I, and it keeps going forever and ever and ever. If we were to add up every single term in the infinite sequence, we would have something called an infinite series. So the series is when we have the sum of all of our terms. We can use that summation notation. We can also write it out this way, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot, dot, dot. That's going to indicate all the terms between a sub 4. Our arbitrary term, a sub I plus dot, dot, dot. That dot, dot, dot implies we're going off to infinity. Or the more common way, we can use our summation notation, where our upper limit in an infinite series is going to be infinity. Now we could also have a finite series where we're only summing the first n terms of a sequence. This is also called a partial sum or the nth partial sum. So a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n and stop. We're not adding any other terms past that. This one we're going to have that upper bound be n. Now your calculator can compute nth partial sums. It's under the math category on your calculator. However, you have to be able to calculate this by hand. So think about a no calculator section on a quiz or a test. You have to be able to do an nth partial sum without a calculator. Your calculator technically can't do infinite sums, but you can sort of trick it a little bit by doing an upper bound of larger and larger values. And it'll give you a pretty close approximation. And for some sequences, it'll actually give you the total sum. But again, you have to be able to calculate this by hand. So that's what we're going to do. We've got two examples. For each example, we're going to find a partial sum and the total sum of our infinite series. So in each of these, we have our summation notation written out. For the first example, we're doing the summation from I equals 1 to infinity of 5 times negative 1/2 to the I. Now that negative 1/2 to the I, we could split that up as to negative 1 to the I over 2 to the I, and then we'll see that it's an alternating sequence like we saw earlier in our notes. But when I want to do the fourth partial sum, I want to rewrite my summation notation. And we'll see that that alternating sequence of negative, positive come out to play when we find these sums here. But I want to rewrite this in my correct notation for the fourth partial sum. So this is the sum from I equals 1. Now it's a fourth partial sum, so that's only going to go up to 4. of our sequence, 5 times -1/2 to the I. So what I want to do is I want to write out a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. So I want to write out the first 4 terms of now a series, since we're doing the sum. So this thing alone, without any sums, that's just a sequence. Once I start adding them all together, then it's a series. So my first term is going to be 5 times -1/2 to the first. My second term is 5 times -1/2 to the second, plus my third term, which is 5 times -1/2 to the third, plus our fourth term, 5 times -1/2 to the fourth. And I want to clean this up a little bit. 5 times -1/2 to the first, that's -5/2. Plus 5 times -1/2 squared, -1/2 squared is going to be positive 5/4. -1/2 cubed is negative, so instead of plus, I'm going to minus 5/8 plus, because -1/2 to the fourth is positive, 5/16. So adding these up, we get a common denominator. You do your arithmetic, you know, making your second grade self very proud of your ability to add these up without a calculator. And we get -25/16. And that is our fourth partial sum. Now, when we're asked to find the sum, that is the sum of this entire summation that we have up here. That is the infinite sum that we're looking at. So when we do this, I'm going to start in a pretty similar way. I'm going to start by writing out some terms. Now, I'm not going to be able to write out every single term. I'd be sitting here forever if I did that. But I can start writing out the first 4, 5, 6 terms. And what I'm going to do is I'm actually, instead of writing them as fractions, I'm going to write them as their decimals. So this first one, was we already said was -5/2. That's -2.5. Plus 5/4 is 1.25. Minus 0.625. Plus 0.3125. Plus ... Now this one we don't end, so we have to do that plus ... And you may not see a pattern, and it's not very clear on this one. When we get down to our last example, we're going to show you one that you're more likely to see, and you'll be able to see the pattern there. And eventually we'll see how to sum this up using a formula. That's a couple of days away though. But this is actually going to add up and become -5/3, or as a decimal, -1.666 repeating. Right? Again, I know I'm not giving you an explanation of how we got to there, and I'm not going to for this example. I'm going to show you one down below where you can do that. You can reason through it a little bit better. And in a couple of days, we're going to talk about a formula to find a sum of this type of series. But the fourth partial sum, you can definitely do at this point without a calculator. Find those 4 terms, add them all up, and you're done. So this last example, and I'm not entirely sure why it says example 7, but this last example here, we're actually going to be able to find the sum, and hopefully you'll understand how we did that. It's going to make a little bit more sense than the one we just did. But we're going to start with the third partial sum first. So I'm going to rewrite my summation notation. This time my I is going to go from 1 to 3, because I want that third partial sum of 3/10 to the ith power. So we're going to start with our first term. We're going to list out our 3 terms. Our first term is 3/10 to the first. Plus our second term is 3/10 squared, which is just 3/100. Plus 3/10 cubed is 3/1000. And again, I have to have a common denominator. I'm actually going to, because these are nice decimals, 3/10, 3/100, 3/1000, those are nice decimals, I'm going to write them as decimals. This is 0.3 plus 0.03 plus 0.003. So we get 0.333, not repeating. Not repeating. Or as a fraction, 333 over 1,000. But I actually want to leave it like this. So it's a non-repeating decimal. It stops. It's 0.333 stop. But that's our third partial sum. And you might already start to see how we're going to do this final full sum of the infinite series. But if I want to do this, I'm going to start same way, but this time we're adding up to infinity. So I'm just going to start by writing my first few terms. All right, my first term was 0.3. Second term is 0.03. Third term, 0.003. Fourth term, 0.0003 plus ... This can keep going. You can see each new term is just pushing that 3 one digit further along the line, one digit further along the line, one digit further along the line. And so when I add these all up, this is just going to be 0.3 repeating. You know, that's that 0.33333, and it just keeps going, never ending, ever stops, or 1/3. So this one, hopefully you can see how we got to that a little bit easier. Again, I know I did not really explain the one above, but we will get to that later when we get to the formula in a couple days. But this is definitely, this last example here is definitely one that you could be expected to do now by hand without a calculator. You can find the sum of that infinite series because we have that pattern showing up. So that was the end of that note sheet. If you have any questions, please let me know. I would highly recommend you get started on this web assignment as soon as possible. You do not want to fall behind in this unit. The homeworks are not very easy. They take a little bit of time. Make sure you get started on them early enough so that if you do have questions, you can come